So as I mentioned earlier, this is module 2. I consider the intro stuff we just finished module 0. Module 1, remote visual inspection, we'll be doing that in lab. So each group's going to have that. The group that'll have lab today, you'll get it on Friday, you'll get it Friday. But we're moving into magnetic particle inspection. That way you've got a background on a couple different techniques so that you can start performing these in the lab. So with all of these, I'm going to start out kind of with advantages, disadvantages, high level, and then move into the technique and the theories behind how they work. So advantages with magnetic particle, it's very sensitive to small flaws. It's good for finding surface cracks. And you can find some subsurface, shallow subsurface defects. The equipment we have is not really the type designed for that. We'll talk about that in a bit. Ours is an alternating current or AC bench. To find deeper subsurface flaws, you have to use a direct current or DC bench, and it's a more specialized kind of sub area of mag particle. It's a very fast process. When you're learning, it's going to take you a few minutes, but once you've kind of got the techniques down, it actually can be done really, really quickly. You're going to be, part of it is you magnetize parts by running current through them or around them. And when you run current through around something, it's essentially magnetized almost instantly. And then you're applying particles either in a liquid carrier or as a powdery dust, and that sticks to the areas where the magnetic field is leaving the part. And so you can see that how long it took me to explain it is longer than it actually takes sometimes to apply and do it. Now the inspection part takes a little longer, but it's pretty fast. Moderate skill to perform. It's not a particularly technical, it doesn't require a ton of training. It's one of the easier ones to learn and get proficient at. There are options, I say semi-portable because there are options for portable equipment as well as a fixed location bench like we have down here. And then it's relatively inexpensive, particularly the portable versions of it. You can buy a yoke, what's called an eddy current yoke, for roughly $600. In aviation world, that's inexpensive. Okay. Student world, I know that's a lot. That's like, a semester's worth of groceries. Probably not even that nowadays. But, it's relatively inexpensive. Now, the bench, the fixed location bench we have, still are relatively inexpensive in that they're probably not more than $10,000 to $20,000. Again, sounds expensive. In aviation, if it doesn't have like 5 zeros after it, it's really not that expensive. Okay. Disadvantages, however, because it is, magnetic is in the name, you have to have ferromagnetic parts or parts that are close to ferromagnetic. Like I talked about during the intro, stainless steel technically can't, most of the time it's said it can't be magnetized. I'm going to blow your minds today and say, yes, you can magnetize at least temporarily a piece of stainless steel, depending on the alloy. You must be able to access the entire part or at least the entire area of interest, okay, compared to some other techniques where you may be able to find flaws that aren't, that are hidden behind other parts or objects or sections of the aircraft. But I did mention in the intro, magnetizing parts carries a risk of overheating or possibly melting and welding. And so you got to keep that in mind, how much current you're putting through the part. What do you think determines current that you can put through a part? What's the number one determiner of it? What? Material somewhat. What? The size of it. Think about wires, right? Low current, you can have tiny little wires. You put a lot of current through it, it's going to burn up. So if you have something like a big crankshaft, you can run pretty much as much current as you want. Our bench cannot overheat, overload a crankshaft. But if you're doing something like a little valve, right, the little valve stem, that probably can't handle the same amount of current as a big crankshaft. Right? So you have to adjust based on that, and there is that risk of overheating and welding. When you're done, you have to demagnetize the part. This is particularly, it's important whether you're in aerospace or not. If you're doing it in like this technique will be used on car engines, on motorcycle engine parts and that kind of thing. What's the risk of magnetic parts inside of an engine if you don't demagnetize them? What? Magnetize to another piece. What in particular could magnetize to it? Contaminants. Say you get metalware in an engine, where do you want that metalware to end up? In the bottom of the oil pan or in the filter, right? If you have a crankshaft that's magnetic, now all those particles stick to it and they get between the journals and the bearings, and now you've got basically grinding metal bits between the moving parts, right? So you don't want that. There's another consideration with aviation. What is the consideration with aviation in terms of magnetic parts? What do we use magnetism for in aviation? The magnetos, parts of them can be, but I think broader. What's that? Flight instruments, navigation. If you have magnetic parts in an airplane, it can throw off the navigation system. In fact, not only did we use the MPI yokes for performing mag particle inspection, when we had a plane get hit by lightning, lightning's a current travels through steel part becomes magnetic, like a landing gear leg, for instance. We would actually use these MPI yokes in their demagnetizing setting to demagnetize landing gear legs, to demagnetize windshield frames. Windshield frames right next to the whiskey compass, right? You probably don't want a magnet right there. Demagnetize other hardware. We had flux gates out in the wings for the navigation system. You don't want those to be near magnetic materials. Visual detection ultimately is required, so it falls on you as the person testing in order to inspect it, and people can make mistakes. I'm going to go ahead and stop there.